Now let's do some physics talk. A wave is energy moving along a medium. Leonardo da Vinci said that the wave flees the place of creation while the water does not. That's sort of a hint to help us understand how water waves are created. A medium is what the wave or energy travels through. The slinky, for instance, was the medium when we sent the pulses along, or when we sent the compressions forward. The slinky was what the wave was moving through. As you're listening to this, air is the medium for your sound waves. Meanwhile, water is the medium for water waves. Our ears recognize amplitude by how loud something is. The bigger the amplitude, the louder something is. If something sounds really soft, then the amplitude of those sound waves is really small. A node is a point on a stationary wave where there is no transfer of energy and the medium is motionless, while an antinode is a point where the displacement of the medium is the largest. We have one equation, which is V equals F times this funny looking Greek letter. This Greek letter is lambda. We also have F equals 1 over capital T. So what these equations mean, V is the speed of the wave measured in meters per second. F is the frequency, which the unit for frequency is a hertz, or 1 over a second. And lambda is the wavelength, measured in meters. Capital T is the period, which is measured in seconds. When we sent the slinky with these longitudinal pulses forward, what we're actually doing, if we look at the bottom image, is we're moving the molecules. The molecules are compressing and then expanding. That expansion is the rarefaction. Take a look at this red dot and notice how the displacement is still 0. Yes, it's moving a little bit to the right, it's moving a little bit to the left, but remember, displacement, direction matters. So the net displacement of this red dot is 0. Same with this red dot. Same with this red dot. The dots are staying in place while the energy moves along. Looking at a transverse wave, where we vibrated the slinky in a perpendicular motion, perpendicular to the direction of the wave, this is what's happening with the particles within the medium. The particles move up and down. They're not moving. The net displacement is still 0. But the energy is being transported through the medium. Here they are side by side. We have the transverse wave on the bottom and we have the longitudinal wave at the top. The equilibrium point is the at-rest point. If this slinky was at rest along the floor, along the table, it would just be a straight line, right? And here again are instances of particles. So with a transverse wave, you can see the particle is going to go up and down, but its net displacement will still be 0 because the positives cancel out the negatives. As the energy moves along to the right, it's just riding along that wave. Same with the longitudinal particle, this red line. It's just riding that wave until it has to go backwards.